Hello everyone, my name is Ashfaq Ahmed and I'm working in the field of structure biology and bioinformatics. I hope most of you are familiar with me because if you are following my channel, so today we are going to talk about computer aided drug designing part 5. We have already covered four part of this course, and in those four parts, in part first we identify a receptor in UniProt and ChEMBL, and in part 2 we downloaded the required data from in part 1 we downloaded the required data, and in part 2 we manage that data and apply some filtration strategies using RO5, rule of 5, I would say. And in part 3, we used uh, some some method to clean our data set from the unwanted substructures. And in part 4, we generated some fingerprints for the filtered data. Today in part 5 we will use these fingerprints and we will learn how to cluster this dataset. But before going to part 5, I want to explain or I want to mention one important question. Few of you guys has contacted me on my personal number and they have asked that is it necessary to keep this pipeline in the same order you are teaching. So the answer is no, it is not necessary. You are allowed to skip part 3, part 4 if you don't want. For example, if you don't want to calculate substructures uh, because of some reasons, then it's okay. You are allowed to skip part 4, sorry, 3. Now, if you don't want to perform some compound similarity, then you are allowed to skip part 4 and part 5. Today we will cover it. So it's not hard and fast rule, it's up to you how to manage your strategy. This course is basically teaching you all the strategies. Now you have to decide which strategy to be number one, or which strategy to be bypass or skip, or which should be the following or number two you have to apply. So I'm just giving you all the strategies, and that is then up to you which one to skip or which one to keep. So let's start for part 5. First of all, as you all know, so we most of we are working uh, for this project and we are using Google Colab. So let's go to our repository. If you are new to this channel, so don't worry, I will put all these links in the description section. Then click here, CADD project. Click here, part 5. Okay, before going to part 5, I also want to discuss another thing with you. I'm For this course I'm using the library of Teach OpenCAD, also mentioned here, and these are designed by someone else, by another lab. The question comes, then why I am copying these libraries here? The answer is I'm not copying A to Z. The reason is if you go there and if you want to run these libraries or these notebooks, you will not be able to run it until and unless you have some substantial expertise in computer science. Um, I'm not going to tell you why you will not be able to run it. So, because this is not our main topic. So, I'm keeping these libraries here with proper references, with proper information, and just because I want people, specifically those working in the field of biology, I want them, I'm trying to make them able to use these library uh, in an easy way. So that's the one reason I'm doing this. Even if I bring you directly into those libraries from where I'm copying it, I will also not be able to run them directly. So I work for them. I make them kind of usable for those who had limited knowledge of computer science. So that's it. So let's start. In today part, we will discuss about the compound clustering. What is compound clustering? It means, in simple words, the classification of compounds or making clusters of compound or making groups of compound. So we call it compound clustering. This is actually the aim of this of aim and objective of this notebook. But why we cluster compounds? This is another question. If you remember, we had picked almost 6,000 molecules from the ChEMBL. So we also then calculated some fingerprints and blah blah blah. We did so many things in previous parts. Now here we will group our compounds based on the structural similarity. But I will not use the structural similarity word further. I will use based on the fingerprints. Now, what are fingerprints? I talked about it in previous video in substantial or in sufficient detail. So, based on fingerprints or based on structure similarity between the compounds of ChEMBL library, we will group those compounds into specific clusters. So this is the main aims of this notebook. You need to collect here, you need to what I would say connect here, and I'm already connected. What we will use in this notebook, we will apply some Jarvis patterning algorithm or Botina clustering. What are Jarvis patterning algorithm or clustering, or what are Botina algorithms or clustering? I will highlight some of the key points here, but for the detailed understanding, if you are interested, references are here, and you can also click here and open it a new browser to read further. So briefly I will explain this document for you. So clustering, as I told you, it's actually the grouping of compounds based on some variable. In this case, our variable will be the fingerprint, or I would say the structure of compound. So clustering is actually the grouping of objects, or and then same objects will be grouped together in a similar or in the same cluster. And we will cluster our compound based on some pharmaceutical variable or some variable from chemoinformatics, and that will be our fingerprints. So compounds having similar fingerprints or having similar structure will be grouped together in one group, and the rest will be grouped separately. This is the main objective. Why we are doing this, you will understand once we finish this notebook. Okay, so this is all about the and what Jarvis-Patrick algorithm do. Actually, if you read about the Jarvis-Patrick clustering, Jarvis-Patrick clustering calculate with some statistical way or some mathematical way, I would say, and it calculates the similarity between compounds, and the value of similarity is that is in K. We call it K value. Then the K value can be explained further into K min and K max. K max means the maximum K value, and K min means the minimum K value. So if two compounds share the K min with each other, it means they are similar to each other, or I would say they are neighbors to each other. And then based on these statistical calculations, we can group these compounds into a single cluster or into a single group. That's it. Okay. One of the drawback of this method is that normally it keeps a heterogeneous compound also in one group. Then another clustering method is Butina clustering. You can read this paper if you are interested. So what Butina clustering do? It's almost the similar as the previous one, but here uh, it it mainly uh, calculates, or I would say it mainly group the homogeneous cluster. So what is the difference between homogeneous and heterogeneous? I know majority of my listeners are undergraduate students, so to help you understanding these two terms, I will refer you, I will bring you back to your chemistry courses, um, like homogeneous solution and heterogeneous solution. So the term homogeneous means similarity with some level, similarity at some level, and the heterogeneous means that they are similar, but on the other hand they are not completely similar. There are differences at some level too. So this was the simplest definition I could uh, present here. So the Butina clustering actually identifies smaller compound or these compounds, but the cluster will be mostly homogeneous, and we will mostly employ the Butina clustering in this notebook. What we will do is very simple, and you will understand somehow. We will upload our data to the notebook, then we will calculate the Tanimoto similarity, and we will group that similarity information into a matrix form. And how to calculate the Tanimoto similarity we have already covered in part 4 in detail, that what are max and what are Tanimoto, etc., etc. So if you have not covered part 4, I would suggest you need to cover that. Okay, and then finally we will cluster based on these similarities. We will cluster our data, and then we will perform some basic analysis between those clusters. In the meanwhile, I will also teach you in this notebook that how to use different cutoffs while generating your clusters. Okay, and then Okay. About this, we will talk in this notebook, so I'm not going to take much more of your time. Now, here we will start installing some packages. So, when you run this script, remember I have also mentioned here that kernel restart will take place. So, it may take 20 to 30 seconds, but at the end of this, your browser or your notebook will take a restart. So, don't worry, it is normal because we are installing Conda and it takes a restart. Also, okay, you see, it is restarting, so it will happen to you also, so don't worry, it will be connected automatically. Now we have installed our Conda. Remember, this tip will take almost 10 to 11 minutes. I'm talking about my own internet, so if you are running a bit slower internet, so it should be in your mind that it may take 15 to 20 minutes. So I'm going to run this step because we need to install so many things. You can see. So I need to pause this notebook and will reconnect you once these programs are installed. So in the meanwhile, I'm not going to waste your time. So welcome back. It took almost 16 minutes. I told you that 12 to 15 or 16 minutes. You can expect this time or maybe 20 minutes. So I tried my level best to reduce this time, but something we cannot do or I cannot do for you. So you have to bear this time for installation or should have a cup of coffee. Okay, so now the programs are installed and we will proceed for some uh, import functions or import job. Okay, that's it. Now here we will load our data prepared in part 2, and if you have followed the part 2 data, if you remember, we performed some Lipinski, we calculated some Lipinski descriptor and we named the data RO5 underscore properties. So I will load that data here. You must have your data in your system, and the data I have is I rename it to RO5 underscore properties 1 dot CSV. Uh, so first upload your data here. When this uploading is finished, the second thing you need to do to fix name of your data. If your data name is something else, so you need to fix it here and then run this cell. You will see this kind of information: molecule ChEMBL ID, IC50, units, smileys, PIC50, molecular weight, and those other stuffs. Now remember, this is the data which follows the rule of 5, Lipinski rule. Okay, now we will create molecules from the smileys because this data contains smileys, so we have already installed the RD kit, so it will create the molecular structure and we will visualize later. Now we will calculate some fingerprints for this data, and this cell has calculated the fingerprints and number of compounds converted 6816. Once again, let me remind you, don't confuse yourself. I'm using data from part 2. Okay, so in other words, I have skipped the the substructure calculation stuff, but if you also want to remove the substructure and then want to use this, then it's very simple. Remove the substructure and then manually, I would suggest manually edit this CSV file generated in part 2 and remove those structures from this data set. Okay, now we will calculate some fingerprints. Calculate it. We will visualize later for in some analysis. Now these cells are just generation of some data sets in the form of different fingerprints. Now this cell is generating distance matrix from the Tanumutu fingerprints calculated here. This cell is just is trying to ensure the elements in a matrix. Now here we will perform some clustering for which this notebook is designed. So we will cluster the molecule, and let's see. Clustering has been performed. We use the cutoff value 0.2. You will understand what this cutoff value means later. Now we are going to cluster the fingerprints calculated, cluster our library based on the calculated fingerprints, and it will gives us such kind of that, like how many total clusters were found. 1000 and somehow 54, and cluster with only one compound, 484. It means total groups or total clusters based on the fingerprint similarity were found 1054. Among them, 484 contains only a single molecule. 246 contain 5 compounds each. 5 clusters are the biggest clusters that contains more than 100 compounds, and 43 clusters are relatively bigger. Each one of them contains more than 25 compounds. So this was a general introduction of the clusterings which were performed by this script. So this is actually the figure of this kind of clustering performed. If you see, 5 clusters are with 100 or more than 100 compounds. So this is the number of molecules. If you see very few lines, in fact these are 5 lines, cluster 0, cluster 1, 2, 3 and cluster 4. They are more than 100 compound, you can see. But other clusters like these clusters, they contain compounds below 50. You can see below 50. Also you can read here 25 compounds are 25 clusters contain compounds 25 or more. So you can see these are those 25 clusters here. Now almost 484 compounds clusters contain only one compound, so you can expect here. Now the next question comes, how we can generate a reasonable cutoff, because this calculation was performed based on 0.2 or 0.3 cutoff. Now, so for the reason we will run this cell, okay, what this cell will do, this cell will calculate all the clusters based on different cutoff. It will use point 2, point 4, point 6 and point 8. So when we increase the number of cutoff value, as a result the clusters will be decreased. You will see now and you will understand. It's still running. This code will generate almost 5 to 6 figures, so I will show you. If we use the cluster 0, sorry, the cutoff 0, okay, from here, because these are many plots, so you will use this sliding bar. If we use threshold 0, or the threshold actually means cutoff, so if you use the 0 cutoff, we have so many, more than 6,000 clusters. These are the cluster index. But on the other side, if you see only one cluster contain, I would say, 5 compounds, the second biggest cluster contain 4 compound. So I would say this is not a reasonable cutoff to select for further analysis, because almost the program has generated all the cluster from the single molecule. Now let's see results of the point 2. Now the point 2 cluster enable us to give us some communities, like the first cluster that generates, uh, it contains molecules more than 120, you can see here, and it also reduces the number of clusters, you can see here, uh, up to 750, I would say. It contains at least more than one compound, you can see here. But and if we suppose these cluster contains only one compound, then you can explain this data this way. Now with cutoff 4, the cluster number are reduced to 200, and let's say this much contains one molecule and this much contains substantial number. You can see many cluster now contain more than 100 compounds, you can see here. So this way it will give you a fair idea, like for further analysis, which cutoff you will use. So I would suggest you to use a cutoff value in your analysis which contains a reasonable number of clusters having more compounds. We do not want to analyze, or we do not want clustering that which generates almost the same number of cluster as our compounds number. So therefore you will decide for your data. In this case I am going with the 0.2, because the 0.2 contain almost half of the data, or a reasonable number of cluster with substantial amount of molecules uh, in the data. Okay, you can also read here. So now I'm going with 0.2. If you are going with 0.4, for example, in your data you are going to 0.4, so do not run this cell as it is. Please change 0.2 to 0.4 this way. Okay, I'm going it to, let's say, okay, I'm doing it with 0.4. Let's say what it happens. Okay, so now it will replot the zero point 0.4 data for me. So let's wait. Okay, with zero point 0.4 you can see uh, one cluster contain almost 800, and then come here 200, also some cluster contain more than 300. So I think it's a good selection. Now we will do some visualization. uh, 10 example from larger cluster. Now let's have a closer look at the first 10 molecular structures of the first largest cluster. Now this is very interesting. This is I plot 10 molecules from the first largest cluster. I mean from this one, which contain almost more than 800 molecules, I just plotted 10 molecules. So if you see, all these 10 molecules are somehow similar. If you think that no, there is some dissimilarity, then you can come here again and rerun it with zero point 0.2. Okay, I'm now rerun the clustering stuff with zero point 0.2. By this step, I'm telling you how you can switch or shift between different clustering options. Now you can see the first cluster will contain 120, and then the second contain 80, and like this. And we have two figure generated here, with one with 0 0.4, the other with 0 0.2. Now visualize again the 10 molecules from the first cluster. Now I think the 0 0.2 is better in my case, because if you see visually from visual inspection, I think all these molecules contains more similarity than the previous one. But that's okay, it's up to you. It's not hard and fast rule. Now save molecules from largest cluster for other talk tutorials. Now I'm saving some molecular data set. Its name will be molecule set largest cluster. So from the largest cluster using cutoff value 0.2, I save this data set in SDF. Okay, later on we will download it. Now we will print 10 molecules from cluster 2. Now I also want to teach you another thing here. Okay, first of all, look to the molecule present in cluster 2. They also look almost similar to each other, as in cluster 1 they were looking similar to each other. Now for example, you are interested in cluster 3, what you will do? But so it's simple. The cluster number starts from 0. So this is the cluster 1, but in reality it is cluster 0, but from the index number. Now this is cluster 2, but from the index number it is cluster 1. So if you want to analyze, let's say, cluster 3, so the index number will be cluster 2. The index number will be 2. Let's say, now this is cluster 3. Now you want to analyze from cluster 5, so the index number will be 4. So this was the way how you can manage to view the representation of different cluster in your data set. Okay, so we will use this information because we have already stored, or we have already saved our data set here that contains the representation of molecules from different clusters, and we will use this in part 6. And in part 6, let me tell you in advance, in part 6 we will generate MCS, maximum common substructure, from a cluster. Okay, and I also want to tell you, in this course I will teach you so many new things. We will come to the machine learning, and I will also teach you how you can optimize your compounds, how can you perform uh, molecular docking and then edit your compound using the same kind of interface like the notebooks. It will be easy for you, so stay connected with me. um, I'm trying to explore or teach you all those tricks and hits and ifs and buts in this course. Okay, now we are going to print 10 molecules from the first 10 clusters. This is interesting. This is from the cluster 1, this is from the cluster 2, 3, 4, 5, 6. So all these represent 10 each molecule from each cluster. If you want to increase the number of clusters, so 10 molecules from first 10 clusters. So if you want to increase the number of the cluster, like from first 20 cluster, just increase this range. Okay. Now we are generating some wait. Okay, save cluster centers from the first 3 molecule as SVG file. Now we will generate some SVG file, but it gives an error and it says that mole SVG is not defined. Okay, let me try where we have made a mistake. Mole SVG, yes, it is not defined, so therefore it is not picking here as mole SVG. Okay, so we need to define first, so let's say mole SVG. Let's try now. Okay, you will have the SVG here after some time, and its name will be cluster representatives dot svg. Okay, now I will also fix this error in the notebook, so you will not face this error while using this notebook. Okay, so you will not face this error. Okay, now we will calculate, or we will look for some intra-cluster similarities, uh, and these scripts will calculate such kind of similarities quickly. So we calculate just the similarities between first 10 clusters, 1 2 3 4 5 6 7 8 9 10. These are the index number. As I told you, it will start from 0, and the 10th index number will be 9. Now for example, in your research you are interested to calculate the tonomoto similarity of first 20 cluster. How will you do it? Because if you change the 10 or 20 in this code, it will not work. It will give you some kind of error. For example, if you say that let me change this range to 20, it will generate an error. Why? Because it plot this data based on, this is the plotting script. It plot this data based on these calculations. So first you need to increase the 10 to 20 here. Now you see I increase this into 20. Now I run this first. Now here we have 20, so now let's say, you can see now we can generate a similarity matrix between first 10 clusters using this kind of Weiland graph or Weiland plot, and it's up to you for how, if you need the similarity index based on Tenemu to similarity among intra clusters, then you can increase or decrease the cluster number in by doing this. Okay, now we are going to pick the final list of compounds. Maximum 1000, could be more than 1000. And how we will pick, we ask the programs like these 1000 should contain the representation of almost all the molecules, almost all the clusters. So here we will run this. Once we run this, so it generates a data set of 1655 compounds. Now you can run this cell and it will sort by size and molecule, and it did it work. So run this cell. It says I have the data of 1655 molecules which contain the representation of almost all the clusters we calculated above. Now in case you want to use this data 1655 in future, so I keep this script for you. It is not present in the original one, so the selected molecules.csv will be generated here. So now we have clustered our data, and we have all these files here. So you are supposed to download these things, and we will use this data in our next analysis and other notebooks. Okay, finally this is some extra work. It has nothing to do with this notebook. If you want to run it, you can run it. It will just tell you how much the number of molecules or the size of data, I would say, how much it affects the runtime in seconds. So if you can see, if molecules are 2000, then the runtime will be less than 2 seconds, but if it is 4000, it's above than 4 second. So in future, if you have a bigger size of data, let's say 10,000, 20,000 or more than that molecule in your data set, so it means how exponentially it impacts the runtime of your calculation. So if you want to run it, you can run these 3 codes. Otherwise it has nothing to do exactly with this notebook. I hope you are liking my videos, and you are also learning something new with me. So support this channel and support to start learn or to learn effectively different tricks and different experiments in the field of computer aided drug designing. That's enough. Have a good time and stay happy. Bye bye.